Hi everyone, my name is Ryan Henry. I'm a graduate student at the University of Florida College of Engineering. I'd like to talk to you about my project this semester where I went over the evaluation of existing facial recognition techniques. So jumping right in, I broke down facial recognition into four major steps. The first being facial detection. For that we use a histogram of oriented gradients in order to detect faces within an image. And then moved on to facial projection, which is actually normalizing the faces found in that image so they can be compared to each other in a one-to-one situation. For that we use landmark estimation in order to determine what the orientation and the size of the face was in the image, and then affine transformation in order to then normalize it once we knew how it was oriented and what size it was. Moving along, facial encoding is the actual extraction of features from the face that will be used in the classifier in order to determine whose face it is that we're examining. For that we use a convolutional neural network, which is very common nowadays for facial recognition techniques. And the final portion is the facial classification. For that I use a support vector machine. It's a very quick and efficient way to classify the images with the output that we're getting from the convolutional neural network. So going into this first process, facial detection. So again, use the histogram of oriented gradients, and for anyone who's unfamiliar with what that is, I'll jump ahead for a second. We are basically going to take an image that looks like this and find the edges in the image by using the histogram of oriented gradients, or HOG, which I'll refer to it from now on for short. And we use this in order to compare it to a face pattern that we are aware of that is made by averaging thousands of different faces in order to find the face in our image. But going back to how to actually generate a histogram of oriented gradients, or HOG, the first thing we do is convert the image into grayscale. The RGB values aren't going to help us find an image. We just care where the edges are, and those happen either at dark sections or light sections, anything that's different from everything else, so edges. So in order to create the histogram of oriented gradients, you examine a given pixel, and then you look at its cardinal neighbors and determine in which direction the pixels are getting darker, and that is your gradient for that pixel. Now what you do, you have to repeat this process for every pixel in the entire image. Once you do that, then you divide all of the pixels into 16 by 16 blocks. And from those blocks, you make histograms. So each of those histograms is divided into 9 bins. So every bin goes from, all the bins in total go from 0 to 180 degrees because you're using unsigned gradients. You're doing that because you don't care if the gradient says it's 0 degrees or 180 degrees, they're both horizontal, so that's all you care about. So use unsigned gradients and to organize these into 9 bins. And then out of these 16 by 16 blocks, you get 4 of them in a square pattern in order to normalize them. So you normalize them by taking the L2 norm of all of the block values and then dividing each of the block values by that. And then you move this block of 4 across the entire image in order to normalize the entire image. Now once you've done that, you should end up with an image you see over here that is a histogram of oriented gradients from Will Ferrell. And then once we have that, we're able to take this face pattern, which again was trained by averaging thousands of people's faces together to show this. So as you can see, the eyes are over here, this is the bridge of the nose, the mouth is here. And so if you convolve that across the image and the size is approximately correct, then you should get a high return, which would be an indication that you have a face in that region. That's a detection. Now, given that the size isn't guaranteed, what we'll do is we'll resize this image into various sizes in order to evolve it across the image in order to try to find any possible detectable faces within the image. Yeah, that's the gist of facial detection. Moving on to facial projection. So once you've located a face, you need to then normalize it so that all of your comparisons will be similar to each other and it minimizes the error you'll get from that. So as you can see here, we use a process that generates 68 landmarks on a face in order to characterize the orientation of the face. So this is done by using a cascade of regressors that modify what shape they're in based on the error they get. So if in the original image this would probably be oriented like horizontally as if my head wasn't tilted here, and then it would try to calculate error values based on where each of its landmarks are, and it would correct for it. It would try to move in a direction to make it better. And then it would repeat the process over and over again until it found itself in a local optima for this. And as you can see, the process works very well. The eyes are dead on, the mouth is dead on, the nose, the jawline, the eyebrows, everything works great. The only thing we actually need from this, for my process, is the location of the eyes. So there are 6 points on each eye, and we're going to average those in order to find the center point for the eye. And we're going to do that for both eyes. By having the center of each eye, we can then calculate the angle of the head. So if we assume that the eyes should be level with each other, you can then figure out what the angle offset is that my head is tilted at. Alright, so once you have the angle of the head, then that is one of the parameters we need in order to make an affine transform, which would modify this image and rotate it and scale it correctly so that it appears like the other images that you're comparing against. The other thing you need is to determine the scale of the image, what the scale factor is for I have to zoom in or zoom out on this image. So you do that in a similar way by using parameters from the eyes, but you have to make assumptions first for how big you want each of your images to be. So for the rotation, I assumed that I wanted every face to be oriented normally. I guess I don't know if you call it portrait style, but yeah, so facing forward, portrait style. For the scale, you just have to declare a set of dimensions for how many pixels you want it to be for width and height. I chose 256 by 256. Doesn't really matter as long as it's big enough. Then you determine where you want the eyes to be located within that region. So I determined that I wanted it to be the left eye approximately 35% down the way from the top and 35% to the left, away from the left, and then vice versa with the right eye. So 35% down from the top and 35% away from the right. And so once you do that, then you know that 35 and 35 are 70%, so you have 30% of the window in between your eyes. So if you then calculate the distance between your eyes on this original image, and you take the quotient of the two, you can then need a scale factor for the image has to be multiplied by. Alright, and then the shift from the image just comes down from where this facial detection region is. So you can also use the center location between the eyes. That's what I did in my process. So the midpoint here is where I said the shift was, and when you include that, then it rotates. The rotation performed with that center, so everything rotates around that point. And then you plug in, now that you know the angle, the scale, and where you want the center to be, you plug it into this formula, and it will give you an affine transform you can use to then transform your image. Moving on to the facial encoding technique. So this is the process where we actually extract features from the face. So everything before was just setting up so that all these inputs would be similar. So facial encoding uses a convolutional neural network. If you're unfamiliar with what that is, convolutional neural network is where you take an image, you then break it up into overlapping subsections. So it's not just perfectly diced into even pieces, so there's a little bit left over in each piece that its surrounding neighbors also have. You then put each of those sections into a regular neural network. Each section goes into the same neural network. They're all experiencing the same weights. You then take that output and you're able to keep it in line with which section it came from. And once you have that, you can group them into groups of their neighbors. So you can take 4 or 9 at a time, or whatever dimensions you like, and you can downsample them. So you say, I only want the sample out of these 4 samples that had the highest values. So out of the group of 4, you take the highest value and you throw the other 3 away. Now you have a downsized sample of the image. You say the high values are where the interesting things are happening in the image. That's all I care about. Now you can do this process in several different orders and repeated many times, and the structure that you create using these steps is what defines a convolutional neural network. I did not generate my own convolutional network. They take a lot of time and computational power in order to train. So I use a pre-trained neural network for facial recognition that outputs 128 parameters for whatever image you put in. Once you have the different parameters that you've input, you can then train a classifier. So I use a support vector machine. It's very fast and very efficient for what we need it to do. So due to the 128 outputs that are generated from this convolutional network, there is a high dimensionality for what we're examining. So, and if you know anything about the, my teacher referred to it as the porcupine effect, but it's once you get into high dimensions, the distance between points grows exponentially. And thankfully for us, the convolutional neural network, if you are putting in the image of the same person, should output relatively similar values every time. So the clusters for each of these classifiers should be pretty tightly clustered, and there should be a large amount of space in between a cluster for one class and cluster for another. That makes it very easy to have this linear divide between 2 classes. Support vector machine is great for that. So support vector machine, as you can see in this example above, chooses a hyperplane that maximizes the distance between the closest point of each class. So it's not going to choose B because it's too close to the blue stars, and it's not going to choose A because that would be too close to the red circles. It would choose a location like C where it is fairly distant from both of them. And that gives plenty of room for other data samples that we're comparing this against later to fit, let's say, in here and still be categorized as a blue star, whereas if we selected B, they would have selected it as a red circle. In addition to this, because it's dividing this feature space in half, everything would either be, in my example, it would be either myself or my sister for what's classified. But you need to be able to determine that, hey, this doesn't look like either one of the things I've trained against. This is unknown. So my method for doing that was to compare the distance from the nearest class member with the average distance amongst the class members. By doing that, if it's outside of some factor times that average distance, you can say, hey, this is too different from the other classes that I've trained against, and we just need to say this is unknown. It looks too different from the classes that we know of. So this process actually works very well. As you can see here, a Christmas picture from my family this year. Correctly categorized myself, my sister, and my parents, who I did not have a train for. I noticed that they were neither one of us and said they're both unknown. Overall results for this evaluation. So I modified how the number of images that were used for training, and the performance started out pretty low with 1 and 2 images, jumped up a bit here, kind of leveled off at around 6, and then jumped up again at 18 and reached its peak at 20 for both my sister and I. This may look like one set of data for most of it, but actually there's 2 sets here. Unfortunately, it appears that my Halloween photo did not make the cut. It could not distinguish that that was me. Anyway, that's all I have for you guys. Thank you very much.